Welcome to today's lesson, series of bioproduct or biomolecule separation techniques. So we will be looking at membrane separation techniques, and from the word, simply these are separation techniques that uses membrane. Just to have an overview, we'll have the introduction, then the principle, types of membranes, the modes of membrane processing, classification, types of membrane processing, the advantages, disadvantages, and how we apply them. So the introduction, the membrane processes are an accepted unit operation for a variety of separations applied mainly in chemical and food industries, and the processes are driven by pressure, modes of concentration, as well as electric force across a membrane, and can be differentiated according to the type of the driving force, whether it's pressure, concentration, electric force. Can also be differentiated by molecular size of what is separated and the type of operation. So the basic unit of membrane separation processes is now the membrane. Very important. This is the basic unit that we are using in all these methods. So membranes are usually semi-permeable barriers that are used to separate two phases. One of the phases is called the permeate that is able to pass through the semi-permeable membrane. And then we have the retentate, which is now retained on the top of the membrane, and it is retained based on the particle size, based on the electric charge and all that. So the two components will be dependent on size, electrical charge, pressure, etc. It performs separation by a combination of techniques such as filtration techniques, purification, sieving, and diffusion. The separation efficiency is usually affected by different processing factors, such as the feed composition. This is now what substance, what is the characteristic or what is the component of the substance you actually want to separate. We can have pH, we can have temperature, pressure that is being applied, the feed flow, depending on how the machine looks like, and the interactions between the feed component and the membrane surface. So the principle behind membrane separation is, now you can see from this diagram here, we have the feed or the substance that you want to separate. Then we have the membrane and we have the permeate. And within here, we have the solid particles that are in brownish, and we have the bluish representing the solvent or the liquid. So the separation is accomplished through the application of a driving force on the solution or this feed. So there'll be a driving force on the feed so that it's able to pass through a specific membrane. And in the separation process, the feed stream is separated into two fractions. We have the permeate, the fraction of feed that permeates through the membrane. Then we have retentate, which is the fraction of the feed that is retained over or does not pass through the membrane. Here, this is another schematic illustration of the membrane separation unit. So you have your feed, then you have the membrane at the middle, then we have the membrane support here. So we have the retentate, which remains on the membrane surface and does not pass through. Then we have what passes through this way, called the permeate. So we have different types of membranes based on the material they are made up of. So we can have organic polymers like cellulose and their derivatives, polyamides. We have polyethylene, polycarbonate, polysulfones, chlorine, fluorine, substituted hydrocarbons. We also have inorganic based membranes such as oxides of silicium, zirconium, titanium, aluminium, and so on and so forth. The principal requirement of any membrane should be that it should have a high permeate flux, or it's able to pass through the permeate as fast as possible. Then chemical stability and being inert, so that it is non-reactive. Then good chemical strength, again, so that it doesn't get destroyed in the process of separation or over time. Then thermostability, maintain temperature, because temperature affects how a substance moves across the membrane. Smooth, resistant surface, fouling resistant surface, so that again it doesn't scratch or trap substances that essentially are not supposed to pass through. Resistance against microbial action, yes, so that you do not have growth of microorganisms with time. Affordable cost, important, and then long service life. So this is a schematic classification of membranes. We had organic, which is we have the polymeric ones, and we have the liquid membranes. We can have dense. We can also have them further classified into isotropic, asymmetric, and composite. Then we have porous, polymeric substances. We have asymmetric and microporous. Then we have the inorganic ones. We talked about them having metallic and also non-metallic, like ceramics. We have different modes of membrane filtration, or ways in which we can pass our feed on top of the membrane. We have the dead end, which is where the feed flow is perpendicular to the surface of the membrane. You can see this is perpendicular. This is the membrane surface and this is the feed. So it's coming from up against the membrane, and this causes a large reduction in flux. Yeah, because once they settle here, it means that the ones that are coming after, maybe the particulates that will come after, for example, when the solvent is likely not to flow as much. So the flux here is quite reduced. But then we have the cross flow, where now we are having a horizontal kind of flow, where the flow of the solution is parallel to the membrane surface. This flow causes turbulence and produces shear against your feed and our membrane, and thus allowing for increased flux or passage through the membrane. We have factors controlling membrane processing. Yeah. So for example, here we have membrane properties affecting this processing, feed properties, and hydrostatic effect. So we look at the various factors against the membrane, against the feed, and against the hydrostatic effect. So if you change the pore size of a membrane, by increasing it, you increase the flux or the allowance of that membrane to pass substances across. If you increase the thickness of the membrane, you reduce or decrease the flux. If you increase porosity or pores, amount of pores you change, if by increasing them, you also increase the flux. If you change the tortuosity of the membrane, becomes more tough, you decrease the flux. If you increase the compaction of your membrane, that actually essentially reduces the pore size, then you reduce or decrease the flux. Now for feed properties, if you increase the concentration of the feed that you are passing through the membrane, you decrease the flux. Yeah, you decrease the flux. Then if you increase the viscosity of your membrane, sorry for that, if you increase the viscosity of your membrane, you decrease the flux. And then if you increase the temperature, the feed, if it has high temperature, then it means that it's going to facilitate the membrane to open and also allow more permeate. That means increase the flux. Then we have increasing the transmembrane pressure. This is now the hydrostatic effect. If you increase the pressure, you increase the flux. And then if you increase the cross flow velocity. If you increase the cross flow velocity, that's the speed of your feed, then you're also increasing the flux. Now, we can also have this classification of membrane separation processes based on the driving force, the hydrostatic pressure or force that you are actually applying on this. So we can have pressure-driven membranes, we can have potential or current-driven membranes, we can have concentration-driven membranes. The main ones we have is the pressure-driven, where we have microfiltration, we have ultrafiltration, we have nanofiltration, and we have reverse osmosis. Potential driven, we have electrodialysis and electroosmosis. We have concentration driven, where we do dialysis. So classification based on the size of the material uh, usually will now result into pressure-driven membrane usage. So we have like the microfiltration, we have this kind of pore size being about 0.1 to 1 micrometers. So this kind of microfiltration will not allow suspended particles and bacteria, but will allow the permeation of viruses, multivalent ions, monovalent ions, and water. Ultrafiltration, which has a slightly lower pore size of 0.01 to 1 micrometers, we have it not allowing suspended particles, it doesn't allow bacteria, neither does it allow virus to pass through, but it allows multivalent ions, monovalent ions, and water. Nanofiltration has a smaller pore size of 0.01 to 0.001 to 0.01 micrometers, and this one does not allow suspended particles, does not allow bacteria, does not allow viruses, then partly allows multivalent ions and allows monovalent ions and water to pass through. Then we have reverse osmosis, where the pore size is actually smaller, less than 0.001 micrometers, which is less than 1 nanometer. This transmembrane does not allow suspended particles, bacteria, viruses, multivalent ions, and also monovalent ions, but it allows water to pass through. And you can see we also apply different transmembrane pressure across these platforms. Yeah, so this is the same now. So there was the differences based on pore size, but you also have differences based on pressure. As you can see, the different pressures that are applied. And of course, what kind of solutes can be separated. So for microfiltration, solutes that can be separated is like clay, paint, oil droplets, suspended matters, microorganisms. For ultrafiltration, we can remove pectins, proteins, high molecular weight, polyphenols, enzymes. Nanofiltration, we can remove sugars, low molecular weight polyphenols, dyes. Reverse osmosis can eliminate electrolytes and salts. Now, the purpose of micro and ultrafiltration is when you want to clarify a crude extract or remove turbidity within a solution. Nanofiltration can be applied in decolorization and purity increase, because you can see we are able to remove even smaller low molecular weight substances. Then for reverse osmosis, we can do concentration and also desalination or removal of salts from solvents. So let's discuss each of them a little bit further. So microfiltration is a low pressure cross-flow membrane process, and it designates a membrane separation process with a larger membrane pore size. So we have more of macromolecules being separated. It separates the colloidal and suspended particles that range between 0.05 to 10 microns. It can be used to remove bacteria, fermentation of broth, clarification, biomass clarification, and recovery. And microfiltration is used as a pre-treatment before you can now do ultrafiltration or even reverse osmosis, so that you remove the crude and clarify and remove turbidity from your solution. Can be applied in food industry, yeah, where we clarify things like beer and wine for removal of microorganisms and yeast. We can remove oil droplets and also fat globules in food. We can remove suspended solids and also fat present in brine used in fish processing. And we can also use it in pre-filtration of wastewater streams generated in food processing. We can also apply it in the dairy industry for making low heat sterile milk, removal of bacteria, and preheating of cheese whey. Then we can also do ultrafiltration, which is now a selective fractionation process that operates under still low pressure of up to 10 bars. And this one lies between microfiltration and nanofiltration in terms of pore size. This one allows the concentration of high molecular weight proteins, macromolecules, and other small suspended solids. Polymers like polysulfones, polyamides, PVC, polystyrene, polycarbonates, and polyethers are usually used as the membrane. So inorganic salts, lactose, and water are removed as the permeate, whereas now the fat globules, the proteins are retained over the membrane. And this concentrated milk or retentate is used in manufacture of things like cheese from milk. So whey protein concentrate is also retained over the membrane, and this retentate is used to produce the concentrations of protein which we call whey. So ultrafiltration can be used for isolated soybean protein production. So you can see this illustration. So you apply pressure, we have the retentate, then we have what goes through as the permeate. That's ultrafiltration. Nanofiltration, size and charge play a role in this process, and it is also known as loose reverse osmosis. It usually has a pressure of about 10 to 50 bar, and the pore size ranges between 0.1 to 10 nanometers. The mass transfer mechanism in this nanofiltration process is actually diffusion. So the NF membrane permeates usually will be things like certain ionic solutions or solutes such as sodium and chloride, also monovalent ions, and of course water will permeate through. Then this nanofiltration membrane will retain a little bit larger ionic species, including divalent and multivalent ions, and of course more complex molecules. So this nanofiltration is used to remove mainly the monovalent ions, partly demineralization and water removal is obtained. So this nanofiltration can perform separation applications such as color removal and also removal of some salt. Then applications for these membranes range from removal of natural organic matter in wastewater, treatment, hardness reduction in water purification, and then whey demineralization or removal of minerals which are multivalent ions that can be done now in dairy processing. This now, what we call the reverse osmosis process, can be defined as a membrane separation process driven by pressure gradient in which the membrane separates the solvent, usually most of the time is water, from all the other components in solution. So this one allows just water to pass through. Yeah, so that means that even now smaller ions are actually removed from the solution using reverse osmosis. So the solvent flow is the opposite of the normal osmotic flow. Normally, normal osmotic flow usually comes from a place where we have low concentration of the solute to high concentration of the solution, or where we have more water concentration to where we have less water concentration across the semi-permeable membrane. But now in reverse osmosis, it's the other way around. So we are coming from a place where we have um, we have more more concentration of the solution to towards the less concentration of the solution, or we are coming from a place where we have low water to where we have more water. So the mechanism of this is that by exerting a hydraulic pressure greater than the sum of the total osmotic pressure difference, because when there's that osmotic difference, the tendency is for the low concentration to move towards the high concentration. So we have to overcome that pressure by applying hydraulic pressure that is greater, and the pressure then loss of diffusion through the membrane that can cause the water to then diffuse in an opposite direction into the less concentrated solution. This is what we call reverse osmosis. The greater the pressure applied, of course, the more rapid that diffusion process will occur. And using reverse osmosis, we are able to concentrate various solids, either dissolved or even dispersed within a solution. The process is used to produce relatively pure water, yeah, in this case pure water, or a concentrated solution of microsolids from a given solution. The membrane configuration is usually a cross flow. We don't do the dead end. Cross flow is the best. So the pressure here applied is about 30 to 60 bar, actually the highest among all these four types that we have looked at. And the pore size is the smallest, it's lower than both micro, ultra, and also nanofiltration processes. And in reverse osmosis system, water is the permeating material, or it's the one that will now become the permeate, and the remaining solution is concentrated with the solids, which we call the retentate. The reverse osmosis is a high efficient technique for dewatering process streams. You can also concentrate or separate now the lower molecular weight substances in solution. You can also clean wastewater to make it clean and free of any substances. It has also the ability to concentrate or dissolved, so including dissolved contaminants and also the suspended solids. So the permeate contains very low concentration of any dissolved solids, and therefore reverse osmosis is typically used to desalinate even seawater. So you feed the water within this system, and then you are able to get clean water. So you can see that once you apply pressure, you have very high contamination within this solution. Then through the semi-permeable membrane, then you just pass the water or have the water as the main permeate substance. The main advantages of all these membrane separation technologies are: one is able to separate streams or components at a lower temperature, minimize thermal damage to the product. We don't have, because we are not involving heat, then we do not damage the products using heat. Separation of this component is in its native form. Yes, if it's cellulose, and it allows substances to move as they are originally. Less energy is used to just using pressure and sometimes now electricity. Then they are easy to operate, then they are environmentally safe, then do not denature things like proteins that are very critical even with shear force. Then no requirement for chemicals, then can remove 90 to 100% of the pathogens in a water sample. That means that this kind of filtration process can actually give you clean drinking water. Then it allows the filtration of any volumes of a non-turbid water from the disk. Disadvantages of this technology is that turbid water cannot be used because it's likely to clog the membrane. Then there may be risks of bacterial abundance as the water carries numerous air microorganisms. Glass filters are breakable and can break easily and quickly. The membrane filters can also crack because they are made of, even some of them are made of organic material. Then only liquids are sterilized by this method. We cannot sterilize, let's say, solid substances. Then filters are costly to repair, especially like the nanofilters. So that can also become another cost. Constitutional restrictions of supplies. used in filters may alter the effectiveness of this process, such as the damage of glass filters, fractured to membrane filters, and consumption of the filtrate. It also requires some pressure. Remember, we were talking about applying pressure. So they require quite a high differential pressure to be able to achieve. And also clogging can occur, which now would mean need to first dismantle the membrane, clean it up, or even replace. So the applications, as we have highlighted as we were coming along, is in industries and laboratories, and it can be used to sterilize heat label food materials. It's also most effective and acceptable method of filtration of drinking water. Then can be used in pharmaceutical, cosmetics, electronics, and also food and beverage industries to monitor um, bacterial contamination. Can be used in wastewater treatment before releasing it into the rivers. Can be used in cold sterilization of beverages. Yeah, because we are not using heat like the beers. Then can be used to separate milk fractions. You can get the whey, you can get the cheese. Can also be used to concentrate proteins at the macromolecules. We can also use it for defeating skimmed milk and also whey to, concentrate them. Then we can also use it for partial demineralization of whey. Partial means because we are not entirely able to remove all the minerals, but at least we're able to remove a greater percentage of the higher molecular and also some low molecular ions. So our conclusion of this is that membrane separation technology serves as an alternative for various conventional methods like the evaporation, where you're removing minerals from water, processes such as centrifugation and other filtration processes that are widely used um, in processing over conventional methods is mainly due to following reasons. So why would we would use this above the evaporation, centrifugation, and other filtration is because we have minimized thermal damage and energy saving and also better product quality. Now, as demand for novel food products or ingredients is increasing, then membrane processing can create novel products and ingredients with desired characteristics. And finally, membrane technology is considered as a green technology. Yeah, because of less use of energy, we use less energy, then we can use organic substances. So because of that, and also because of their efficient energy utilization, where we don't need chemicals and any other additives, then it's considered a green technology, which is good for our environment. So those are membrane separation technologies that can be applied in the various industries as well as in any biotechnological work. And those are some of the references in which you can refer this work to get more insights. Okay. Thank you. That is the end.